Okay, it's now time to talk about the characteristics of waves, but also learn how to calculate the speed of a wave. Now, a wave is a repeating disturbance or movement that transfers energy through matter or space. So, for instance, a vibration is a repeating disturbance. It can cause a wave to begin to move, and that wave movement transfers energy. It takes energy from one place to another if it's going through matter or space. Now, medium is the matter or the substance that a wave is transmitted through. So what it's actually passing through, okay? To explain what medium is, think about those little Jell-O fruit cups. You know those cups that have Jell-O and fruit suspended in the Jell-O? Think about that the fruit's medium is Jell-O, okay? So the Jell-O is what the fruit is sitting in, and that's kind of similar to what a medium is for a wave. A medium is what the wave actually travels through. Now, if you have a sound wave, the medium is air, because as I'm talking and you're listening, that sound wave goes from my mouth to your ear through air. Earthquakes, which are seismic waves, they use earth as their medium, so the ground is their medium. Waves on a pond or water waves use water as a medium. Now, waves that require a medium, that have to have something to travel through, are called mechanical waves. Sound and seismic waves and water waves cannot be found in outer space because there's no medium. Outer space is a vacuum. There's not a medium there for them to travel through. Now, one common characteristic between all waves, though, is that they all transfer energy. Okay, that's very, very important to make sure you know what waves transmit or transfer. Now, there are two main types of wave groups. You have mechanical waves and non-mechanical waves, just like we did energy. So first, we're going to focus on what the mechanical waves are. There are two types. They're transverse and longitudinal. So let's look at transverse first. Transverse waves are when the particle moves perpendicular to the wave motion. And I'm going to show you what that means in just a moment. Now, transverse waves have a crest and have a trough. And we're going to draw this in a second so that you can have those labeled. Longitudinal waves are waves in which the wave motion is parallel to the particle motion. And a longitudinal wave doesn't have a crest and a trough. They actually have compressions and rarefactions. So let's look to see exactly what these two types of waves look like. All right, this is a picture of a transverse wave. Can you see that a transverse wave is actually going to move from left to right of your screen? But the particles in the wave are moving perpendicular. They're going up and down. That's what makes it a transverse wave. The dotted line through the middle of the wave is just your medium. So like if this was a water wave, right, the medium would be water. So that's just showing you a medium, that it goes up above the medium and down below the medium. Now, above the medium, the highest point above the medium is called a crest. The lowest point below a medium is called the trough. Okay, so you need to make sure, go ahead and draw this in your notes so that you make sure and you remember how to label this picture, because you'll have to be able to for your test. Here's a longitudinal wave. Now, a longitudinal wave also moves from the left of your screen to the right of your screen in motion when it's in motion. And as you can see, the particles are actually like, and we can show this in class so that you actually have a visual, but the particles move left to right also. So they're moving parallel with the longitudinal wave motion. Now, where the little parts of the waves are all squunched together and all compressed, that's called a compression. When the spring-like parts of the wave spread out and have more space in between them, those are called rarefactions. Also, make sure you draw this and label this, because these drawings will also help you understand the characteristics of the wave a little bit more. Now, one thing that all waves have, or I'm sorry, a couple of things all waves have are wavelength, frequency, and amplitude. Wavelength is how long a wave is from crest to crest. And we're going to talk about that in just a second. Or trough to trough. If you have a longitudinal wave, the wavelength is from rarefaction to rarefaction, or compression to compression. The frequency of the wave is how quickly the wave passes through a certain time. So basically, how many waves can go through in 5 seconds, or how many waves can go through in 1 hour. That tells us the frequency, which is how many waves travel in a certain period of time. Now, amplitude is the measurement from the medium to, for a transverse wave, the amplitude is from the medium to the crest, that measurement to see how high it goes, but it's also from the medium, a measurement from the medium to the trough to see how low the wave goes. So that's the amplitude for a transverse wave. The amplitude for a longitudinal wave is rarefaction and compression. Now let's look a little bit more into wavelength and frequency. Wavelength is the distance between two consecutive crests or two consecutive troughs, and that's what we've already been talking about. The frequency is the number of complete wave cycles or complete cycles per unit of time. So it's just how many pass through in a certain amount of time. Let me go ahead and label wavelength for you. Now, the red line represents wavelength, and it can go crest to crest. You can also draw it trough to trough. It can go either one, but it's just the wavelength, so this would be a measurement, and it's going to be in meters, just like distance, because it is the distance of a wave, okay? Now, I also drew some green arrows to show you amplitude. Going from the medium to the crest is amplitude, but also going from the medium to the trough is amplitude. Now let's look at longitudinal. Longitudinal, its wavelength is compression to compression, and I may have drawn it a little bit longer than it should be, but also rarefaction to rarefaction. Those are wavelength. Again, they're measured in meters. They're going to be like a distance because it is the distance of a wave. Now, we've already talked about what amplitude is on a transverse wave, but here's the definition. It's the maximum distance the particles are moved from their rest positions. Rest positions is going to be where the medium is when they're not moving, right? Amplitude on a longitudinal wave. We've already talked about this. The compression, or when the coils are bunched up. Rarefaction, or when the coils are stretched out. And that is measuring the amplitude on a longitudinal wave. Now let's talk about the speed of waves. We can calculate that just like the speed of a car or the speed of a person. The speed of a wave is equal to wavelength divided by time or period. Sometimes they will say period instead of time. Period just means time, the time it takes for a complete cycle or wave oscillation to occur. So those words can be used interchangeably. Now, so wave speed equals wavelength divided by period, or wave speed equals frequency times wavelength. It just depends on which information you have, which formula you'll use, and we'll show that in the video in just a moment. Now, the speed of a wave also depends on the medium. The medium can slow it down or help it speed it up. Now, the order from slowest medium to fastest medium is gases, liquids, solids. That seems backwards, I know, but waves travel the fastest through a solid than they do gases. So that means earthquakes or seismic waves travel much faster than the sound waves that you're hearing. Now, let's go ahead and do some practice of calculating. Okay. Let's look at this practice problem, but first I want to explain what each of our variables equal. V is going to be speed, just like it always has been for us. F is going to be frequency, which is measured in hertz, Hz. And hertz is actually just 1 divided by seconds. That's all it is. Wavelength is this lambda symbol, this weird symbol. It kind of looks like almost a weird drawn giraffe or something. But anyway, the lambda symbol equals wavelength, and wavelength is going to be in meters. It's going to be the distance, right? And then T is going to be our time. Now look, these were our formulas. Speed equals frequency times wavelength, and wave speed equals wavelength divided by time, and then our appropriate circles. Now this is what I'd like you to do. I want you to pause the video. I want you to complete this question on a piece of scratch paper or on your notes, but make sure you write down the formulas and their circles in your notes. And then resume the video when you're ready to see the answer. All right, guys, as you notice in the problem, we look to see what they're wanting. They say they want the speed of a wave, so we put a question mark next to V. It tells us the waves are 6 meters apart. Meters is distance. Distance is wavelength. So our wavelength equals 6 meters. And it tells us it passes a person every 2 seconds. So the time is 2 seconds. So that means I have to use this formula over here because I have wavelength and time. So I've got V equals wavelength divided by time, and I fill in my numbers. So we say 6 meters divided by 2 seconds. So that means my wave speed is 3 meters per second. Write down any questions you have so you can ask me once we get to class. Now I would like you to do this practice problem. Pause the video, complete the problem, make sure you understand how to calculate it, come back to check your answer. All right, let's go ahead and solve this. It tells us calculate the speed of the wave, so that's the question mark. Then it says a wave traveling on a string has a wavelength of 0.10 meters and a frequency of 7 hertz. Okay, so that tells us we have to use this formula, right? Because we have frequency in hertz. So we say V equals frequency times wavelength. Not frequency in hertz, we have frequency and wavelength, I'm sorry. And we fill in our numbers. Our frequency is 7 hertz times our wavelength of 0.10 meters. Once you calculate this, this shows you the wave speed is 0.7 meters per second. All right, this concludes our video. What I'd like you to do is I'd like you to do your summary now. I want you to write down the 3 most important points of this video. Have a wonderful evening, and I'll see you in class.